Okay, in this section we're going to talk about a particular type of Markov chain called regular Markov chains. But before we do, let's return to an earlier example. If you'll remember our product share example from the previous section, we had this as our transition matrix. Now let's examine the first few state matrices that we might come up with. So if we take the initial state matrix that we had earlier, 0.9, 0.1, and multiply it by this transition matrix, we got 0.62 times 0.38. And then when we took that and multiplied it by the transition matrix for S2, we got 0.72, 0.28 approximately. And then when we did found S3, we got 0.74, 0.76. And then S4, we notice we're getting 0.74896, 0.25104. And then if we do S5, once again we would just take the initial state matrix and multiply it by p to the fifth. That's one way to get it, so that you don't have to go through each step here. We would get 0.74972 times 0.250208. And then of course here you can see S6 is 0.7499584. 0.2500. So it looks like it's converging to 0.75 and 0.25, or 3/4 and 1/4. So that's where it looks like it's heading. So what actually happens if we were to find the product of this S value? So in other words, we're going to say the final S, if we kept going, was going to be 0.75 and 0.25. Now what happens if we multiply that S by the transition matrix? Well, notice that when we multiply it by that transition matrix, we actually get that state matrix S. So it's interesting here that SP actually equals S. And we call S the stationary matrix, since multiplying it by P does not change the output. Let's repeat this with a different market share. So instead of 0.9, 0.1, let's say 0.95 and 0.05. Okay. Now, if we do that, you can go through this yourself. Just take S0 times the transition matrix and you get 0.79. Then take that times the transition matrix, you get this, and then take that times you get this, and so on and so forth. And again, even though the market share was changed, the initial market share was changed, it still seems to be converging toward the same matrix. And again, SP is giving us S. So basically that defines what's called a stationary matrix for a Markov chain. And so if you have a state matrix S0 where it has S1, S2, S3 and so forth, up here we just have S1 and S2, but it's a stationary matrix for an Markov chain if when you take S and multiply it by P you get S. So this matrix right here is actually a stationary matrix, because when you multiply it by the transition matrix you actually get the same matrix S. And now not every Markov chain has a unique stationary matrix, so we need to be aware of that. So let me read this again. Not every Markov chain has a unique stationary matrix, but those that do have a unique stationary matrix does not mean that the successive state matrices will approach the stationary matrix. So just because they do have a stationary matrix, it doesn't mean that when you multiply them here you'll actually get that matrix. So this leads us to the definition of a regular Markov chain. A transition matrix is said to be regular if some power of P has only positive entries. A Markov chain is a regular Markov chain if the transition matrix P is regular. Okay? So in other words, the transition matrix has only positive entries. Now this transition matrix is regular because all the entries are positive. This matrix here, which I'm going to call here on this matrix, this would be an example of a transition matrix that does not satisfy the conditions. So if you want to calculate some other powers of this, but this matrix p to the first is not a regular matrix, and neither is p squared, nor p cubed, nor p to the fourth. So here, no power of p has all positive entries, so this is not regular. This matrix is not regular, but if you produce enough powers, like if you square it, you still don't get a regular matrix because 0 is not positive. But if you get it to the cube power, now you've got all entries that are positive. So in this case, p is regular since a power of p has all positive entries. So it's not just that p has to be regular, it's as long as some power of p can be regular, then we can say that p is regular. Okay, look at the properties of a regular Markov chain. So let's say P is a transition matrix for a regular Markov chain. There is going to be a unique stationary matrix S such that SP equals S. Given any initial state matrix S naught, the state matrices SK approach that matrix. That means if you keep doing it enough repeated trials. And then the matrix P to the K approach a particular limiting matrix, and we call that limiting matrix P bar, and where each row of P bar is equal to the stationary matrix. Now let's see that in an example. Okay, this matrix we can find the long run behavior of this matrix. So what we can do is, what we want to do here is, for this transition matrix, we want to find S such that SP equals S. So we want to find S1 and S2 so that when we multiply it by this, we get S1, S2. Well, if you multiply this together using matrix multiplication, you get 0.7 S1 plus 0.2 S2 for the first entry, and then 0.3 S1 plus 0.8 S2 for the second entry. Well, then you can say, well, this entry must equal S1, and this entry must equal S2. And now let's go to the next cell. If we subtract S1 and S2, well, if you subtract S1 from 0.7 S1, you get negative 0.3 S1, and we still have plus 0.2 S2 equals 0. And if you subtract S2 from the second equation, you get 0.3 S1 minus 0.2 S2. And now we can solve that system. All we have to do is solve the system to find S1 and S2. Now we can throw in order to help us solve this, we know that S1 plus S2 has to equal 1 because they're probabilities. So we can actually put these three equations together and we can solve the system on a calculator. And if you solve this system, you'll actually get that S1 is 0.4 and S2 is 0.6. So I'll let you row reduce that matrix to find that. Now, so therefore the state matrix here is 0.4, 0.6. Now, since that's the state matrix, then the limiting matrix P bar would be the matrix where every row is just 0.4, 0.6, and that would be called the limiting matrix. Okay, let's return to our traffic ticket example. This was our transition matrix, and we know we need the matrix S such that S times P equals S. So we can do what we did in the previous problem, and we can get basically 0.23 S1 plus 0.11 S2, 0.77 S1 plus 0.89 S2 equals S1 S2, and then create the equations, subtract the S1 and the S2 from the right from both sides, and then throw in the S1 plus S2 equals 1, and then you can solve this matrix get the reduced row echelon form of that matrix, and you'll actually get that S1 is 0.125 and S2 is 0.875. Therefore, the state matrix is 0.125, 0.875. So the answer to the question here, what percentage of drivers are expected to receive speeding tickets during any given year, that would be 12.5%. And that is kind of an interesting answer there. Now on the next example, freeze the video and read the example, and then when you're ready, hit play, and I'll start talking about the solution. Okay, if you've read the problem, you saw that the probability that someone goes from C to C, which would be needs improvement, is 90% chance. Those that go from C to B, valuable, is 10% chance. And nobody goes from C to A, so it's a 0% chance. And then if you do B to C, you get a 15% chance. B to B is a 60% chance. B to A is a 25% chance. And then A to C is 0. A to B is 0.15. And A to A is 85% chance. Now, what I want to do is do what I did before. This time I need 3 columns in this S matrix. I multiply it by this and then set it equal to the S matrix. And remember that S1 plus S2 plus S3 must equal 1. So if we multiply these two matrices together and then throw in that other equation, S1 plus S2 plus S3 equals 1, then we get this system. And then if we subtract S1 from both sides here, S2 from both sides here, and S3 from both sides here, we actually get this system of equations. And you can use technology to solve that system for S1, S2, and S3, and we get that S1 is 0.36, S2 is 0.24, and S3 is 0.4. So S would be the matrix 0.36, 0.24, and 0.4. So in the long run, 36% are rated as needs improvement, 24% as valuable, and 40% as exceptional. And so this might be helpful in our professional development program to know information like this. The last thing I want to show you is that we could raise the transmission matrix P to powers until we find the limiting matrix. So if we take this matrix P, so let's just take this matrix P, notice all the rows add up to 1, and raise it to different powers. I squared it, then I cubed it, then I raised it to the 4th power, and so on. And then I got P to the 8th, and then when I multiplied that by P again, I got P to the 9th, and I found out that both of those matrices had exactly the same values out to 4 decimal places. And since those P to the 8th and P to the 9th repeated the entries out to 4 decimal places, then I know that this must be the limiting matrix P bar, and so just pick the row. All the rows are the same, so pick this row, and there's your matrix S. So that's the matrix S. In other words, that's the matrix S, such that SP equals S. And so again, what we could say is that in the long run, whatever this state is, we would expect 49% to reach that state, about 15% to reach this state, and about 36% to reach this state. Now, in the next chapter or section, I'm going to talk about a different type of Markov chain called an absorbing Markov chain. And I won't spend much time on that, but we will talk about that just a little bit.